All right, so we will continue. This one will be the chapter 3. So we'll just kind of go over different types of diodes. So far in our discussion, we see a diode that's usually referred as a rectifier diode. So that's what the name of that diode is, which is usually symbolized like this. We can simply refer as a diode, or it can also be referred as a rectifier diode. So the purpose of this diode is pretty much it can be forward bias, reverse bias, depending upon whatever the biasing voltage is. So you require more than 0.7 volts to forward bias this diode. But there are some other types of diodes are available. Even the type of diodes are very plenty depending upon applications. We're gonna briefly go over very important diodes, which usually referred as special purpose diodes. But the behavior of a diode in general is exactly the same. So that means these diodes also be forward bias and reverse bias. But the major difference will be how they will react. The first diode in that line is referred as the Zener diode. It's in short, we can also say the Zener. So as you can see, the symbol of the Zener diode is pretty similar, but instead of a flat line at the end, that line is usually kind of like a Z, like that. So that's an indication that the diode is a Zener diode. And of course, the terminals are the same. So you see that anode and cathode. So that's the anode and this is the cathode. So the main reason why we use a Zener diode is it has a capability to maintain a specific voltage across its terminals even though the line or load changes. This means pretty much we can use the Zener diode as a voltage regulator. We kind of talk about these voltage regulators after the filter stage in a power supply, but Zener diodes are definitely capable of handling that. So based upon what the model number of that Zener diode is, because every model number is different, especially for the Zener diode. They are not all the same. Unlike rectifier diode, so if you say rectifier diode, all the rectifier diodes, irrespective of their model number, is exactly the same. But for Zener diode, changing the model number will completely alter a voltage value on the Zener diode. Because for example, if you require a 5 volts voltage regulator, then you have one specific type of Zener diode. If you require 100 volts on the Zener, then you have a specific type of Zener. So the main application is it can be used as a voltage regulator. But when, in what bias, this is how a Zener is different from a traditional diodes. Zener is designed to operate in reverse bias. It's not intended to operate in the forward bias condition. So in the forward bias, a Zener is exactly same as traditional diode. There is no difference. So that's why Zener diode means the intended operation is only reverse bias. In forward bias, Zener has no difference in relation to traditional diodes. So it's still 0.7. Yeah, so it's still 0.7 in the forward bias. So it's exactly behave as a normal diode. That's why if you want to use this Zener, and most of the applications, Zener is used as a voltage regulator. That meaning that it has to be wired in a reverse bias condition. And it's usually referred as of course, from the diode terminology, we know it's referred as a breakdown region. So another main difference internally is that Zener itself is a heavily doped semiconductor. Unlike traditional p-n junction diodes, they are usually lightly doped. But this one is a very heavily doped, so the barrier will be very high. Remember that even that 0.7 we are seeing, that's the barrier, correct? That the 0.7 that you need to overcome in forward bias, it's still called as a barrier voltage. So Zeners, since they are heavily doped semiconductors, their barrier will be extremely high in value. Unlike, it's not going to be just 0.7. It could be 5 volts, it could be 10 volts, it could be 20 volts, it could be 100 volts or 400 volts, depending upon what the model number of it. I will show you some of the Zener diodes and their ratings. So there are two types of breakdowns exist in the Zener, unlike traditional diodes. Traditional diode only sees avalanche breakdown, what we call as where you can damage it. So that's usually what is avalanche means. It's where if you apply very high voltage in the reverse bias, you can damage any diode pretty much. But when the Zener is concerned, Zener has another breakdown. In this breakdown, the Zener is going to act as a voltage regulator. It's referred as a Zener breakdown. Remember, breakdown is just a term that uses that we are operating in the reverse condition. So occurs in a Zener diode at low reverse voltages. But if you put a very high reverse voltage, of course, you can damage the Zener diode as well, like traditional diodes. But it's very hard to damage a Zener diode. The voltage requirement for Zener, it's a very high compared to the traditional diodes because of the doping concentration is extremely high. So the damage voltage under reverse conditions is extremely high. So you're talking about, like, depending upon the model number, it could be like more than 100 volts. Unlike traditional diodes, you can break them down around 50 volts, like that. Yes.
I remember the doping methods for normal diodes is about 4 to 1. Is it like a 4 to 2 or 1/2? Is it, what do you mean, like that type of?
For traditional diodes, it's equally doped for both P side and the N side.
Then it was like 4 silicon to 1 doping material, remember?
Yes, this is going to be extremely high.
So
Again, the type of material that the Zener is made up of, not necessarily going to be silicon. Because if you use a silicon, that only gives you a barrier of 0.7. So the Zener diodes are made up of completely different material. It could be like gallium arsenide. So it's a compound material to give us that extremely high reverse voltages. Right. So this is the characteristics of a Zener diode. So if you observe, if you remember, first of all, if you remember traditional diodes, traditional diode characteristics is like this, right? So all you need is, like, say 0.7, and you are in the forward bias condition. So this is like when you are in forward. And when you are in the reverse, so this is usually your breakdown. So I'm going to call as a breakdown. So this is the reverse. So Zener, you can see that these are kind of almost equal to one another. So in the forward condition for Zener, these two are exactly identical. So these two, so this is traditional diode. This one is for Zener. So under the forward, both behaviors are exactly identical. But when you connect in the reverse breakdown, and this is what will happen. So you keep on increasing the reverse voltage. You see that the current passed by the Zener is extremely small. This is exactly like a normal diode, right? Because remember that in the reverse condition, diode will not allow the current. So does the Zener. but only until you reach a voltage called as the breakdown voltage of the Zener, which is usually referred as the Zener voltage. This is usually given by the manufacturer, so we would know only when we refer the data sheet. So what you're going to expect is, as you keep on increasing the reverse voltage, you hit a point where you will hit a voltage where the Zener breakdown occurs. That could be 3 volts, 4 volts, 10 volts, 20 volts, 400 volts. It's whatever the model for the Zener diode is. But what will happen is, when you hit that VZ, now the Zener will allow the current completely under this reverse condition. But you must hit that VZ, right? So let me show it to you. So take a look at this circuit on the multi-sim. So I have a Zener diode which is connected in what type of biasing? So you can see that, so this is the positive side of the source, but it is on the, this is the Zener polarities, correct? So definitely this Zener is under reverse bias because you have positive wire to the negative, correct? But observe the voltage on the Zener is 3.545. Voltage on the resistor is around 8.5, correct? If this is a traditional diode, what this voltage should be? The resistor will get 0, the diode will get the source voltage. If it is a traditional diode, correct? Because traditional diodes will block the current in the reverse bias. But since this is a Zener diode, this specific model of the Zener diode, which is 1N4729A, this Zener diode has a Zener voltage of 3.54 volts. That being said, as long as you are under reverse bias, as long as your incoming voltage is larger than the VZ, so this one is the VZ. So this is nothing but the VZ. Let's take this away. So this is nothing but the VZ of that particular diode. Again, it's related to a specific model number. So let me quickly go through this. So this is 1N4729. Take a look at this sheet right here. So the second one is the one that I have right there, 1N4729. You see that the VZ minimum is 3.42, typically 3.6, max is 3.78. You can see that down the line, there are some Zener diodes they can handle. Again, this is only few diodes I have, but in the textbook on page 118, you will see a lot more. You see that some of these diodes has like 50 volts of VZ, meaning that, so let's focus on just this model for now.
Maximum reverse. That's not reverse. Is it minimum reverse? Is that considering the amount of reverse voltage?
It's considered, so this voltage is the voltage you will see on a Zener diode under reverse bias if the source voltage exceeds the Zener voltage. Remember, what is voltage regulator? So let me quickly see what is this voltage regulator. So let's say, for example, I have a voltage regulator of, so this is a regulator. Let's say I have a voltage regulator of 5 volts. So this one is voltage regulator. Again, when we say voltage regulator, the purpose of a voltage regulator is to maintain its voltage on the output side. So for example, if I say I have a 5 volts regulator, this is what it means. If I have an input voltage of 3 volts, what do you think the output voltage is?
Why would it be 5? You said maintain the output voltage.
So the concept of regulator is if the input voltage exceeds the regulated voltage, then it is going to maintain the regulated specifications. If the input voltage is less than that, like anything below 5 in this example, then it's gonna just pass it through. But that's the sole purpose of a regulator. So anything above, for example, if you feed in 10 volts, so ideally speaking, it should maintain that 5 volts. Right? So that's what a regulator is. So no matter what happened, no matter there are some changes at the input, no matter there are some changes on the load perspective or the temperature, like external temperature the device is operating. So under any circumstance, a Zener diode or a regulator should maintain its regulated voltage, whatever it is designed for. If it's 5 volts, it's going to maintain 5 volts. If it is 50 volts, it's designed to maintain 50 volts. If input exceeds, for example, if input is 3 volts, you see that it's not going to give you 5 volts. It's not an amplifier, it's just a regulator. It's not going to make signal bigger. But if the signal is bigger, then it will regulate it. Yes. So anything higher than 5 volts in this case you will be back to the 5 volts. So that's what the operation of a regulator is. So when you use a Zener diode, as you can see that now the Zener is connected in reverse bias, correct? So that means under reverse bias, Zener is going to act as a regulator. So how much that regulated voltage is, according to this model, the regulated voltage is around those values. So yeah, typically 3.6. So when you look at this multi-sim, you see this VZ is how much? It's within the given specifications because the input voltage is definitely higher than the VZ of that particular Zener diode.
So does the Zener diode, does it dictate the output voltage?
Yes.
For the whole circuit?
Across the Zener. It's the voltage across the 3.54 is the voltage on the Zener diode. But of course, that will determine definitely because now the rest of the voltage is going to be on the resistor, correct? So 12 minus 3.54 will be on the resistor, which will obviously give some current in the circuit, correct? So if I replace this Zener diode with different model, obviously the whole circuit will be affected because its VZ would be different, right? So it maintains the constant output voltage even when the current flowing through it changes. Meaning that, for example, if I change this resistance to something else, then your current will be changing, correct? But Zener will still be maintaining its voltage across its terminals, despite of, even if you raise this to 15 volts, on the Zener you will still see 3.54. Where the rest of the voltage goes onto that resistor. So that's why usually in a design we need to make sure that this resistor should be able to handle extremely high power. Otherwise you could easily damage that input resistor because the rest of the voltage. So if you put 50 volts right here, then approximately 46 volts will be 46.5 will be on this resistor, right? So the power rating of the resistors must be carefully observed, usually when you're designing a circuit with a Zener diode. Yes. Only when you, yes, when the reverse bias. So take a look at these 4 circuits and you will clearly see the operation of a Zener diode. What bias the first one is? So that's positive to the positive, correct? So this is the anode and cathode of the Zener. This is positive and negative for the supply. So forward bias, you see the voltage on the Zener is around 0.55 volts, which is similar to a diode, correct? Because in the lab, that's what you would, yeah. 452 milli is 0.55. So you see that is behaving like a traditional diode under forward bias. That's all. But the rest of the 3 circuits are under reverse condition. So I'm still using the same diode model 1N4729. We know that the typical value is around 3.6. So you see that the input voltage is now how much? 10 volts, which is higher than whatever the VZ is, correct? So you see that voltage on the Zener is still 3.53, which is close enough to the typical value. I raise the input to 20, still reverse bias. The voltage on the Zener is still 3.56, something like that, which is close to the typical expected voltage. But observe the last one. How much is the source? Which is less than the Zener voltage, meaning that
How does it overcome the breakdown? I mean, does it have really small breakdown though?
That's what I wonder, like, shit, completion is everything.
that's why if you under this condition, correct? That means if you are below the Zener voltage, it is also like a regular diode which will block. Remember the characteristics. If you are below, you see right here, you are below VZ, right? You see current is very minimum, like a traditional diode too, until you hit that VZ. Yeah, on this Zener, it is 3.6 is the typical value. So anything below this VZ, this diode will block the current like a traditional diode. But once you pass that VZ, that's where the regulating action will happen. Because circuit is open. No. So voltage on the diode is same as source voltage, correct? So because you are below the VZ. Yeah. So if you are below the VZ, it's still going to block the current like a traditional diode. In forward bias too, it's a traditional diode. But once you passed the VZ value that the diode is designed for, then it will act as a regulator.
So that means that it's going to be a closed circuit.
Then it will be a closed circuit and which will allow the current pretty much. Right. So for example, let me pick, let's say this for simple. So 1N4740, which has a typical VZ of 10 volts, right? So let me give you an example. So let's say that Zener voltage is, so let's say the VZ is 10 volts. So let's say I'm going to have this circuit, Z for Zener. So let's say I have 20 volts and VZ of this Zener diode is 10 volts. So what is the voltage I'm going to read across this VZ? Because first thing is you need to look, is the Zener reverse bias? So that's the first condition, is yes, it is reverse bias. Second condition is, does the source voltage, so does the source voltage is greater than, of course, greater than or equals to the VZ? If these two conditions are satisfied, the voltage across the Zener diode equal to whatever the VZ of the given diode is. In this case, it is going to be 10 volts. Right? So 10 on the Zener, that obviously means the rest of the 10 volts is across the resistor. Remember Kirchhoff voltage law, so when you add these two voltages together, it should be the source voltage. So that's pretty much what a Zener diode is. So if the source voltage, let's say if it is changed to 9 volts, so let's say the source voltage is changed to 9 volts. So what is the voltage on the Zener? So on the Zener, you will see same as the source, because you did not overcome the, it's actually you did not overcome the barrier voltage that it is designed. Yeah. Now resistor will not have anything at 9 volts. Yeah, so voltage on the resistor at 9 volts would be 0.
So where's that rest? Oh,
And of course the current would be what? Current would be 0 at 9 volts. So until you hit the VZ under reverse condition, then only you're going to have current. Then only the Zener will act as a regulator. So